Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and here's another video of the final 4-pole kit. Well, the final for now. So this is the same thing as we were showing, or I was showing the other day with the dual stacked motor here. So in this case we have the same coils on here as here, but we have, like we normally have, 4 motor coils and 4 generator coils, just like the kit comes with. Now this is exactly how it will come right now, but there will be some options. Now in this video what I want to do is show the RPM. I put a piece of tape on here so you can see the shaft acts as a reflector, the tape as a creating a frequency. So now what we're going to look at is running this at 12 volts only. We don't need to go into the other voltages. We've seen that already with the bigger motor, and we just want to look at, this is the input battery at 1270, and this is the charging battery at 1166, and what we have is a 100 watt LED module here. It's going to run at about 25 volts, and full brightness is 33 volts, and it has a bridge rectifier before it, and all these generator coils are hooked up in series with each other. Now I have it disconnected to start. We're going to look at the RPM, and I haven't run these batteries yet, so they've been sitting for a couple of days like this, and so we're not going to have to wait on the battery voltages. You can see they're not going anywhere. Now what I said in the last video, what we're going to do now is keep the generator coils the same as the motor coils, and in this case I put them all in the same direction so that we could at any time convert these to motor coils. Now I've cut the wires shorter so they would have to be lengthened again to make them all motor coils if we wanted to do that. Or we could make 2 of the coils motor coils and all 6 of them generator coils. So now we want to look at a couple of voltages in the RPM, and now I've placed this Hall sensor just slightly to the left, and you'll see that it actually starts in the wrong direction, counterclockwise a lot of the times, and actually that way it started correctly. So you can see it pulls that battery down because it draws a good bit of amperage to start. So the other thing that I've done is, actually the rods that came in the box from my supplier this time were shorter. So I have to make do with those right now, and actually it's probably better that they are shorter. And so what I did is I reduced the gap even further on my gap between the magnets and the rods or the coils. Now I only have maybe not even 1/8 of an inch after the flange part of the spacer. We're looking at less than 1/8 of an inch. Now what I found was the best way to cut these little spacers was just to use an X-Acto knife on the shaft, and that makes an easy cut. A really sharp blade there. Now if I go too close I can't get this Hall switch underneath there. So I'm looking at, oh, I should measure that. Well, it's less than 1/4 inch of a gap now between. It's probably about 1/4 inch then, yeah, between the rods and the magnets, which is fine. Now, as I said, what we're going to do with this center, well, with all the hubs, I'm going to reduce the size, the width of them, so that, and I'm going to make that set screw a little bit closer, so that we can have a nice small gap when we stack these. So now I have this driving circuit here, as I showed the other day, and that's worked out really well. And we put it all on one board now to make it easier. Now, what else? Let's just get started. I'm going to put the oscilloscope on. We'll just put it right across the MOSFET, the drain. Make them connect it. Hold on. So let's look at some things, RPM and so forth. So like I said, we're going to just get it started. You can see, even in that short amount of time, just that startup drew considerable amps. So let's look at this. Let's turn our meter on and off so it doesn't time out on us. I'm not sure how well we can see this in the video, but I'll tell you the amperage here. So we're going to start it up. I just have to turn the switch. So I wanted to go the other direction. So it's about 7-8 amps startup on the meter. So we have a pretty high charging on this battery. So let's start looking at some numbers. We're at only 800 milliamps, 1235 on the input battery. This is going to go down. So we're at 3,700 RPM. Now we have the coils just disconnected, the generator coils. 750 milliamps right now at 1236 volts. Now notice as the amperage goes down, the charging rate goes down. So we're pretty much stabilized right now at 4,000 RPM. Hold on, I'll hold it here. $4,030. So it's going up a little bit more. 4,050. It's pretty fast. Now this thing was going a lot faster at 48 volts. So now let's go to shorting out the coils. Let's just get our final RPM. You can hear it's ringing again. It's gone through several resonant rings, points here. So 4081, 83, it's pretty much stabilized now, 4081. So now, let's short out the coils and see what happens. So now we can look at the spike, we can look at the input. The input's going down, 0.72 amps, 700, 71. $4,400 and climbing. 700 milliamps now. So we're at 4,000 and climbing, 4,500, 600 now almost. 4,585. It's a pretty fast motor. You wouldn't think so by looking at it right now, because you just think, oh wow, it's. I mean, you could almost pass that for a couple hundred RPM by the sound of it, because it's not very loud. So 4,600 RPM. $4,610, 13. So yeah, it's pretty much stabilized now. 4,612. 14. 4,614 RPM. And that is 690 milliamps. So now, what we want to do is short out and look at this light here. So what I'm going to do is turn out the big light, all the lights actually. We'll turn out all these lights here that are very bright. And then I'm going to hook up this. So let's see it one more time before we change over. Still 690. 4,614 still. So the RPM is stabilized. Now let's go over So now we're going to look at this very bright light. That is quite bright. And it may be blinding the camera. So I will turn it. Let's turn it at the motor. Oops. That way, oops. All right, now let's look at the voltage on this. On this light, on the AC side, we have 24.55 volts AC. On the DC side, .67. So of course this is not full brightness by any means, not even half, but it is something. And then we want to look at actually the RPM. Let's turn the light back on. So under load, we're still at 3,594 RPM. $3,593 as shown there, 94 as shown on my tach. So we still have a pretty high RPM here. We're not loading these coils down. And we're at 770 milliamps. So it is drawing more under this particular load. But it is of course charging more. So that's what's nice about this system, is whatever you dish out, you get back. So now we want to look at a couple of voltages here under open voltage. So like I said, 3,000, first of all, 3,592, 93. All right, so let's remember that. And go with, so now under no load, we hear it speed up. Well, this is kind of hard to do. So let's look at the voltages here, not get shocked. Open voltage is 28.5. 0.6 and climbing. We have 730 milliamps right now. 28, 29 volts right now, open voltage. And again, these wires are all 23 gauge wire, so we have the same motor coils as we have the generator coils. You can see we've got some sparking going on here. And let's look at the RPM now, as we started with. Starting to short each other out there. All right, so we're at 4,070 RPM and climbing. And that's really what we're after. Now, we go a little bit higher voltage, we'll get up to 5,000 RPM on this if we were to be at the full charge in this battery here. So 4,080 RPM. Under the shorted condition, this would probably go about 5,000 RPM if this battery was sitting a little bit higher. Which I guess we can do with the bigger battery here. Let me see if I can do this one of these batteries, slightly higher voltage. Just want to check if I got another battery here that's sitting at higher. Yeah, I don't have one here sitting at a higher voltage, so anyway, so there you have it. Let's check one more time. 4,083, 84 RPM. And then all we gotta do is turn it off. So you can hear that ring. So of course, so actually this was sitting at 90 milliamps, 80, 90 milliamps higher than what it was. It's really about running about 64 milliamps with this particular setting here with all. If you adjust it, that will change more or less. So now you can see that this is closer, these rotors, so there's more of a drag on it, but it's nice because it is self-starting. So I think this is what I'm going to keep the kit at right here at with these generator coils. I think I can go with 20 gauge wire as well if I can get some, and I will do that because we're sitting at open voltage 28 volts on the generator coils, so we can cut that in half and still have, you know, a 12 volt charging scenario. So, you know, half of 23 gauge wire is about 20 in size, and so, or doubling it in size actually. So we could get bigger wire on there, and or we could actually just parallel these up instead of putting them all in series. So that's probably better to do that than in using smaller gauge or bigger gauge wire. So we can do that, play around with that, see what we want to do there, and get really all the load out that we want to get with this motor. So if we have, let's see here, so you can see the voltages kind of stabilizing, coming back more or less to where they were. So we were at, let's just say, 0.65 amps at 12.3. So we were at 8 watts, and we were definitely producing 8 watts worth of light on this module here. We were not at 50 watts of brightness or 25 watts of brightness, that's for sure. But it was very bright. You get a 10 watt bulb here. I could probably do a comparison. I got a bunch of these with the regular meter or adjustable power supply there, I can do a comparison. I have a light meter, and we can see the amount of light. Like I said, what you want to do is you want to run this, you want to run bigger modules. Now, the 20 watt ones are more reliably better quality than the 100 watt ones. You'll find that many of the 100 watt ones, as I mentioned, are only as good as 20 watts. And I think that's really the rule of LEDs now, is that they push the LEDs a lot harder. I mean, they have cheap quality, of course, but they push them harder than they're rated for, so they die faster. They're not 100,000 hours anymore, people. But anyway, like I said before, even if you get good quality ones, you want to run them up to maybe 75%, and then not further, because then you're just producing a lot of heat. So they're pretty inexpensive, so you might as well get overrated ones and run them underrated to get the power or the amount of energy efficiency that you want to get. So this easily produces what we put into it. Like I said, we can run this at higher voltages, and oh, I didn't check the temperature on these coils, but they are cold. Obviously at that, we're not even talking a quarter of an amp on those. So that's not a problem. But anyway, we can push this a lot harder with the higher voltages. But remember, as I said with this other video here, the input wire going into the driver part of the circuit needs to be isolated. For those who have the kit, you'll understand that you need to isolate that wire and go and keep it at 12 volts, unless you put a voltage regulator there, which then will consume a little bit more energy. But if you want to put that voltage regulator on there, I think I've got ones that go up to 60 volts, so you could easily take this up to 60 volts. 48 may be the limit on running this, depending on the type of load that you're running. If you're loading it down, it's going to draw more amps, and then the coils, like I said, you want to limit it to half an amp per coil. So that gives you 2 amps. Like we showed it with this one, the higher voltages will draw a little bit more amperage. And at 48 volts, I think we were already at 2 or almost 2 amps. So you could take this up to 60, I think 48 volts. It doesn't really matter when you're looking at the voltages, what voltages you run it at, if you're just swapping these batteries around. If you are because then you could still run really whatever voltage output that you want to run with either series or paralleling these generator coils. If you want to run them at 12 volts, for example, you know, the 12 volt input output on this side is fine. But you go up to 24 volts though, you're going to have considerably more voltage on these generator coil output, as we saw with this one. So what else to say here? So I think we can run this, if we run 48 volts again on this, we can get, I think, let's see, do a quick calculation here. So if we were at 48 volts at 2 amps, then we're at about 100 watts. So right now, like I said, we're only at 8 watts. 12 point, what was it, 3 times 0.665 around. That's 8 watts. So like I said, 24 volts, we're going to be up a little bit higher amperage. Say 1 amp is 24 watts. Right, now it's going to be quite a bit more RPM here. I mean, like I said, we're already at 4,500 RPM, 4,000, 4,800, depending on how we're loading these down. So I didn't check the RPM with this one, but it was up there. It was no doubt, well, I don't even want to estimate. So at 36 volts, we're probably at probably about 1.3 amps, and that would be about 50 amps. Input, output, and then of course, like I said, 48 volts if we went all the way up to 2 amps. Now I think it was about 2.3 amps. So that was a little, pushing it a little bit hard, depending again on the load that we're running. So I think we were showing that with this one, it can run a little bit lighter than that, like 1 point something. So anyway, a 100 watt system. Now if I make that gap a little bit tighter, I can get a little bit more out of these generator coils. I think I can go a little bit closer. I do have a little bit more gap with my hull. And you can feel that magnetic lock. It's not too bad. Like what you want is it to glide over, but you can still feel it. You can hear it. You can. That's more of an ideal location, but none of this is ideal. Ideally, we would have a very big disc and a lot longer off time, and there's a lot more ideals that could be done, but it's not practical. But anyway, the point is, we want to figure out what's practical, which is getting more output for the cost of these parts and so forth. So I think reasonably we can make this easily a 100 watt device, 100 watt continuous output. Like I said, stack it 4 times and you got your 400 watts, and that's enough for the average world daily usage. So that's pretty nice. Now, we could go up to a higher voltage. We just have to maybe then put the speed control on there and keep that amperage down, you know, limit the current. I have to be careful how I limit the current so I don't affect the charging rate. So again, for those who don't know what I'm doing here, this is an over unity device. This is charging up another battery at the rate that the other one is discharging, so these batteries can be switched around periodically. And then we are getting a mechanical load out of this, which can be whatever we desire it to be. So you can see the voltages are kind of stabilizing, or they're coming back to where they were. This one was 1166, I think it was, and this one was 1270. So I didn't run it for very long, so voltages will probably come back. So again, this is all, the way I've been selling this kit has been along this method with the MOSFET for, what, 3 years now, 2 years now? Well, actually no, with the Hall and the reed switch for about 3 years, was it 2012 or 13? Sorry about that. 2012 or 13 I started this motor, so yeah, it's quite a while ago. So 4, maybe 5 years ago, we did the reed switch here, but it's a little bit more involved, so I went to the MOSFET, or we went to the Hall switch first, and then the MOSFET, and now we got the gate driver on there. So it's pretty much at its final place along those lines. And then of course, if you looked at my video the other week where I was showing running one coil as a bifilar coil, and then running that, we can do our third stage process with that, and our second stage as well with the multiple batteries. So this is giving you 2 outputs for 1 input, pretty much exactly now. So this is a nice stable system. So it really doesn't matter if this input and output on this side doesn't match this exactly, because the problem is, or not the problem is, the outputs are completely isolated from each other. I mean, they are not completely isolated in the sense that the generator coils are influenced by the motor coils, no doubt, as I've shown that before. But even if this wasn't exactly the same as this, like in other words, the motor output into this charging battery doesn't have to be exactly the same, as long as these two are the same. The charging rate and the discharging rate. Actually having too much power is more of a nuisance in that case, because you have to then figure out what you're going to do with the extra charge. And having a system that will just rotate around is nice and convenient, and then you have your output. And this one, it's good because it can self-start. So that's nice in this case. This is where when we double stack it, it doesn't self-start as easy, and that's where I could put another external coil on it and pulse it to start it. If we wanted to do a mechanism where we have this turn off, like for example, we have a regulator on here that monitors a particular usage, like we have this going into a charging battery here, like we normally do with the little capacitor pulsar system that we have. Then as that battery gets fully charged and there is no load, then we can just switch off the motor and then have it come on when we need to. And so this is one of the benefits of having it run a single stack system here. So if we take this up to 100 volts input, which we can do with these MOSFETs, and limit the current a little bit and keep it at 1/2 amp each, then we can do this 200 volt, 200 watt system in this. So I haven't done that yet on this particular model, and I just have to make sure that the coils don't get too hot and limit the current that way. So anyway, that's what we can do with this model. Now, like I said, with the trigger coil option, which is what's going to be coming with this kit from now on, one of the coils will be called the master coil, and it will have the extra winding the 23 gauge wire in parallel. So one of the coils will be a master, and then what will happen is you can then run at least one or all of the coils with the what we call the negative energy charging, and that way you could do these other experiments that I've been showing over the last year with the 0-volt process on the charging side, and there's a lot more coming along those lines, people. It's just in its right time. There's a progression that I want to make here with all this stuff. So anyway, the idea will be to have this as a system. In the end, these generator coils will produce a whole lot more than they are doing right now as we add additional processes. Like I said, we've focused this year on doing the loving path circuits where we run the motor in series with two battery banks, like for example 24 going into two 12-volt batteries, and then swapping them around back and forth while we're still charging a third battery bank. And then I showed what we can do possibly on the output side, and there's a whole lot more to that, and that's in development. It's coming. You can see I've been showing you guys more and more, and at my conventions I go into a whole lot more detail, but there's still a whole lot more to come along those lines. And then, so that is something that can be, the trigger coil itself, we can actually do a whole bunch of engineering just on that part of the circuit, which this doesn't have the trigger coil on it on this one. But then we have, like I said, the loving path circuits. We've got a multiplication of the energy out on that particular second stage process, as I've called it. So it's not exactly one-to-one in that case without adding additional processes, but it is definitely more efficient, considerably more efficient, that you could run those battery banks back and forth at least 5 times, and then get a whole lot more energy out than you would have just running one battery bank to the charging battery bank. So again, that's we're talking about 3 banks there. We still continue to charge the output for what we're putting into the system, but in that case we're running the second stage process, which is the third battery bank. So, and then like I said, if we run additional processes, we could keep those 2 battery banks swapping back and forth. I think it's a bit too much batteries for a lot of people to go that route. This route right here is probably the preferred one that people have wanted to do over the years. I mean, this is all that people have known maybe over the years. But this is less battery and easy to do. Now, the other thing is I have to make the battery switching device. I have basic regulators right now, or the latching contactors that we use. We just time them to switch. And I think ideally with this one, you would actually run it for a little bit. We're charging up a battery constantly, right? So we can afford to turn it off for a minute at least when we switch the batteries. That way we give the batteries a little bit of time to come back naturally to their position, and then switch them, and we could just have it switch back on a minute later or 2 or whatever. Let it rest for a bit. 5 minutes would be great to give the battery some rest, to go from charging to loading. And then, since we were constantly charging this battery, it shouldn't really matter if we're off you know, for five minutes or something like that. Because normally people don't run a constant load, they run various peak loads. So, so yeah, that's what can be done. And then, of course, like I said, in the end, I'm not going to say when or how quickly we'll get to that, but there'll be some more very special surprises. So these generator coils will be found to be very useful in the end, that we'll be able to produce kilowatts from these as we add additional processes. So this is a very useful tool, and it's something to really learn from in many ways. There's many things to learn from this. So for now, I'm focusing on getting a really efficient circuit and getting all the particulars down here that we want, so we can stack this up and then not have to go to the really big model. I think it's just out of a lot of people's price range, and you know, if you could have even a couple of these, you know, that particular 4-pole, the bigger one, or the 10 coiler, is significantly more cost, but of course it does, you know, hundreds of times more output than this model. So you have to realize that. But I think this is something that I want to focus on more now, because it's really enough to provide a lot of power to people if they, like I said, stack it up. You could run definitely all your lights off of this. There are certain shops around the world that run all their lights off of these, and so it's easy to produce light, of course, as we saw with these LEDs here. And then we can multiply it out as much as we want. So I think that's all I'll say today. And one more check of the, oh, it's at 0 RPM. So thanks for watching, and come back for more later.